If you guys remember what all we have discussed in last class, we finished all till here concurrency and long and all is done. And the other side, we did all of this. So today what we'll do is we'll try to design certain entity relationship diagrams. And what we'll do is we'll see how to convert those entity relationship diagrams into a table. And we'll try, if time is left, we'll try to go through normalization also. We'll take some examples of normalization and try to do them as well. So the first question is, we want to design a entity relationship diagram for a car company. Sorry, for an insurance company where you are filing the insurance money for any accident that took place. Okay, how will we do it in that case? Okay, so first of all, who all will be our entities? I mean, who all are the important people in this? People, wrong to call people entities.
Customer.
Okay, customer. Uh, Customer is, you can say, whoever is the person who's driving the car. Okay, let's call it person. Okay. So what do we do? Entities, we put them inside a box. So entities are designed like this. Okay, and then entity will have different properties. So let's say somebody who is driving the car. What is the first thing they need to have?
Driving license.
Yeah, driving license. So properties are put inside a circular box. So let's say it's DL. And primary keys are usually underlined. This is- Okay. So driving license is one, and he'll have his name, and let's say he has his address. Okay. So if the driver is one person, then there should be, what does he drive? He drives a car, right? So car can be another entity. So person, and we have a car. Person, what is the relation? Let's say relationships are put in a rhombus kind of a thing. Rhombus only, and let's say person drives. Car, again, what are the properties of a car? A car will have, again, it will have its number, and number is a primary key. Number, I mean, license plate. Okay. Let's say I have circle here, and let's call it license plate. And what is the model of the car? Okay. Car is one thing. Then, so if somebody is going to claim a money, what is the thing that would have happened? The thing that would have happened is accident, right? So let's say we make accident another entity. Accident is another entity. So let's say we identify an accident by report number, and then we have where the accident took place, is location, and when the accident took place, let's call it date. Okay. So all these three together will lead to what? Will lead to an accident happening. So this person as a driver, this car, this accident, they together participated in this all together accident. Uh, you can say take part in an accident, participated, and then out of it you have a, let's say, a damage amount. So what is happening? A car insurance company, when you're if you're designing, it can be any different. I'm not saying this should only be the way. So I'm referring to one diagram and I'm teaching you this. So and so they're defined it like that. So you have a person, you have a car, and then you have an accident. So person relationship between person and car is the person drives the car or he owns the car. And then accident, there is no relationship. Accident is related to a person and car such that they took part in that accident and there is some damage amount. Okay. So now if you are going to convert this into a table, how do we do it? So we'll first create tables for all the entities. So there are two types of entities that we discussed before, right? Strong entities and weak entities. So here all of them are strong entities. If you remember, strong entities are put in a rectangular box like this, whereas weak entities are in double rectangular box. So what is a weak entity? For a weak entity, it does not exist on its own. It needs some strong entity which should be present so that the weak entity can exist. Like for example, let's say you have you have loan, you've taken a loan from a bank, and then you have an installment. So when will this installment exist? This installment will exist only if you have taken a loan, right? So let's say, like for example, you have a test. Okay, you have an exam for a test for a subject. So when will this exam exist? Only if there is a subject. Let's say the subject is science. Science exam is there. So when can you conduct a science exam? Only when there is science subject you can conduct a science exam, right? So here what happens? Exam becomes a weak entity, whereas this what subject becomes a strong entity. Something similar to that. So here what we have done is we have taken all these three as strong entities only. Okay. So since all of these three are strongly typed strong entities, what we'll do, we'll create a table for all of them. So let's call the first table person. Okay. And then what are the properties? You have a DL. DL is primary key. And then you have a, what do you say? Uh, you have a name, address. Okay. And here, if you look at this relation, right, this relation can be like, if I take one person will at least own one or more cars. So I can say one or more. So at any time, if the relationship is like this, right, where one and there are more on the other side. So that time what we do is we take this entity's sorry sorry. So we take this entity's primary key as a foreign key here. So how will it be for car? So car will have let's say the foreign key will be what? The foreign key will be DL of a person, and then we have the license plate. Let's call it LP, and then you have model, and then you have yeah, license and model only those. So DL and LP here. So DL becomes the foreign key, and LP becomes the primary key of this table. Okay. So then you have again accident. Accident again has a report number. Let's call it RP, and then location, and then date. So this is not related to anything, so not put anything. So this is the relation that is happening here, right? Participated and damage amounts. How we'll design this? So we have person. So if I would make this table that time, how will it be? Let's say let's call it damage amount table. How will it be? We'll have DL number of the person who was there, and then let's denote foreign keys with all double. Okay, this is double. So DL is there, and what was the car that was there in the accident? So it becomes LP. And then what was the accident ID? So it becomes RP, and then damage amount. So this becomes another table. So how many tables we have now? We have 4 tables. So for this kind of a diagram, we had three entities, and all the three entities were related for for this damage amount. So what we did, we took out all of them and we
Sir,
created one table.
how we have decided for damage amount in that columns TL?
I have decided for damage. DL. So a person is participating in this, right? So there is a relationship between person and this. Person is required, car is also required, and accident is also required to claim a damage amount. So that is why we have taken the primary keys of all these other entities and added it here. We look at another example. So the other example is very big. So let's say we have a hospital, and in hospital you have patients who are taking tests. There's a hospital, and in the hospital you have patients who are taking that. There's only one hospital, so you have patients who take tests, and these tests are administered by doctors. So these tests are taken by doctors. Okay. So then how will we uh, do a diagram for this? So first of all, let us identify who all are the entities here. Who all will be the entities? One is
Patient,
patients.
doctor.
Okay. So you have patient is one entity, and then you have a doctor who is another entity. Let's say I need to remove this. So you have a doctor, and then you have tests, right? The test, I mean like blood test, or let's assume urine test, or you have whatever different kinds of tests that can be performed in a hospital, right? So test. So you have test. So who performs the test? Doctor performs the test. So can I say the relationship here is doctor performs the test, patient takes the test, and then between patient and doctor, uh, so doctor has to give back some report. No, let's say doctor monitors the patient. So now let us then try to say what are the different, how will we identify a patient, and how will we identify a doctor, and how will we identify a what do you say, a test. Okay. So patient, let's say he'll have patient ID, let's call it PID, and written it like this. Then you have what else we have? Patient will have a patient name is there, and he has a date. So when patient comes to a hospital, right? So when did he check in? When did he check out? Or check in, check out. No, date admitted and checked out. Okay, admitted, and then you have checked out. Okay, so this for patient. In test, what will you have? Test, you will have the test ID again, ID of the test, name of the test, and then you'll have mm, results of the test.
Yes, sir.
And doctor you will have again. So ID is there for most of the people. You have the doctor ID, and then you have the name of the doctor, and then you have, let's say, what is the specialization. Okay. So one thing is, so any test, the relationship if you see between test and patient. So a test is totally dependent on the patient, right? You cannot conduct a test without a patient, right? And you can
Yes.
conduct one test, one patient can, we can do multiple tests for a patient.
Yes, sir.
So one is to many kind of a mapping is identified by a arrow like this. And then if let's assume if an entity will, if an entity has to be like, how would I put it? Uh, so if an entity cannot exist without, if in a relationship, this entity is always, patient is always needed for a test, right? So then what we do, we add a double line. So this is called as total participation. So what total participation means is, if I want to conduct a test, I'll always need one patient to conduct the test, right? So it's like that. And then similarly, one patient will be monitored by one doctor, and let's say different doctors can perform different tests. Cool. So how will we, this diagram that I've done is very clumsy. Let me show you the actual diagram. Okay. I was to take the actual diagram. And what should I be? Actual diagram will look something like this. So you have a patient, right? Execute. You have a patient, you have a test, you have doctor, and doctor has all these properties. And then you have a test has all properties, and patients have all these properties. And then you have a connection between patients and test and doctor and patient. So patient to doctor is one to one. Let's assume there is one doctor will look at one patient, and only one doctor can conduct one test. So it's again one to one. But one patient, many tests can be performed for a patient. Okay, for one single patient, you can have many tests. So if I was to convert this into a table, again, how will we do it? So first is who all are the entities here? There are three entities. Patients is one, and then you have a doctor, and then you have a what do you say? Um, test, right? So patient will have patient ID, And if one patient is always looked after by only one doctor, let's say, then how will we do it? Or let's say it's not one to one, it's many to many. Okay, so uh, one patient can be looked after by many doctors. So then it will slightly change. So then we'll have patient will be normal patient ID and all these properties we'll add. And doctor will also have all different properties, doctor ID, and so on and so on and so on. Tests, because every test has to be there for a patient, what we will do is we'll have patient ID in test, which will be a foreign key. Okay. And then you'll have a test, it will be for a this is there, and then you'll have the test ID, test name, and all. Date, name, okay, all this. Okay. So now if I want to check what is the combination between patient and doctor, I can see, I can create one table saying doctor patient, patient doctor mapping. Okay. Patient doctor mapping will be, so for a particular patient, who are the doctors? So I'll do PID and then I'll say doctor. Okay. We missed one more thing. Hmm, this also, here we also can have the doctor ID. So we'll have a DID. So because there was a test which it was conducted for this patient, then it was conducted by whom? So that can be put here, a doctor ID also saying this test was conducted by this doctor. Okay. So let us take another example. Can anybody suggest what do we, if you want to take up something special and discuss? Anybody have any preference? So we can do it for that Twitter only, right? So Twitter, what all entities we had, and we can try to get tables from entity diagrams. Okay. So let us say Twitter, what all were the entities? We had tweets, and then we had person, users, and then we had tweets forgave, persons forgave, and then we had comments. Okay. So, so user does a tweet, say user posts tweets. Okay. And for a tweet to exist, there has to be a user. So I can say it's a total dependency on user. Then similarly for comments, uh, who will do a comment? User comments. User comments. User writes. Let's say not comments. We call it writes. User writes comments. Uh, and comments are written on what? Comments are written on a tweet. So how can we say here like this for it? So we'll say comments on say like this. So again, for a comment to exist, a tweet should always be there. So I can write this. Are you guys following what I'm saying?
Yes, sir.
Okay. Okay. Cool. So if you were to take this only and convert it into a table, how would I do it? So you have a users table. Let's say it says user ID. Okay. And then you have tweets. So because tweets always depend on a user, so a tweet will always have a user ID and tweet ID. Okay. And a comment is always, let's say comment is also uh, comment is also an entity, but a comment always needs a user and a tweet should be there so that a tweet, it is done on a user and it is done on a tweet. So you can say comments and so whatever is the tweet user ID, tweet ID, and then comment ID, and then whatever is the value we want. So basically, this is how we keep designing the ER diagrams, and then from ER diagrams we convert to table. So I've not prepared any slides, but came across a very good article which says how we can convert a ER diagram later on into a table. So I'll just share that with you. We can go through it together. Okay. Uh, hmm. So, hmm. This was the one. So there are few steps that are involved when you're doing conversion from ER diagram to a what do you say to a table. So we'll go through all the steps. So first is for all the strong entities, right? So what is a strong entity? Which doesn't need any other entity to exist. So it can exist on its own. So those kind of entities are called a strong entity. So whenever we have a strong entity, we create a table for all of those strong entities first. So like in this case, no. So all these three were strong entities: Twitter, tweet, user, and comment. They always strong entities, so we can create a table for all of them. Okay. So like for example, they're done here. So you take a strong entity and then whatever are the attributes for them, you create a table for that. So once you have done it for the strong entity, then find out what are the composite attributes for that strong entity. So what do you mean by composite attribute? So like for example, address. Address cannot exist on its own. Address has smaller properties like city, street, and house. So instead of writing address altogether, you can break it down into city, street, and house and write that inside the table. Okay. So first is you take all the simple attributes of the strong entity and then create a table with those. Then you add all the composite attributes and then add them to the table. So once this is done, we take all the multi-valued attributes. So what are multi-valued attributes? So things like your phone numbers, let's say even if we are supporting multiple addresses, or as in a college, it's like saying a student has multiple subjects. So we take those kind of values and then we create a separate table for it. So, and how are multi-valued attributes shown? Multi-valued attributes are shown with this double circle. Okay. So for multi-valued attributes, we create a separate table only. So how will that be? So this student has roll number and city as his main properties, but mobile number is a multi-valued property. So what we do is we create a separate table using the primary key and then the multi-valued property. So it becomes roll number and mobile number. So here what can happen is one student can have, what do you say, more than one roll number together. Okay. Then whatever is the relationship, right? So these relationships will be transformed into, we'll see if we need a separate table to look at the relationship, or we can put the relationship in the same table only, like whoever is the depending one. So this is done by looking at different properties. So those properties can be, is it one-to-one mapping? Is it one-to-many mapping? Something of that kind. Okay. So here, if you see, like lot of employees will work in a department. So here employee becomes a separate table, department becomes a separate table, and whatever is the relationship, right? So that relationship is mapped in a separate table again. Okay. So here you see employee number, department number is taken from both of them, and then you have a sales column. Okay. Then if there is a relationship with different values, right? So in those cases, we'll see how it is done. So if the relationship is M to N, right? So we will surely need a separate table. Why we need a separate table? Because you cannot map them in a single. You cannot map them in two tables, saying A1 and B1 will depend on each other like that. So one table will be for both of the entities A and B. The other table will be for the relationship between these two tables. Okay. And if the ratio is 1:n, right? So I was saying how. So every B will always have A. It is saying like that. So then what happens is the second table, no, the second table B will always have A in it with the relationship whatever it is. So here you can see the first table is an independent table. The second table has the A value also present in it, because we know for there'll always be only one A for many items of B. And if it is ulta, again same. So here it is many to one. So since it is again many to one, this B will be separate. B will only have B1, B2, whereas A will always have one B for itself. So it is A1, A1, B2. Okay. And if the relationship is 1:1, you can either have A on B side or B on A side. So uh, so again we'll have so cardinality constant is what is the number? Is it 1 to n or 1 to m or 1 to 1 like that? So participation constant means, so there can be two participation constants. One is partial and one is full. Full means total participation. Partial participation means maybe there or may not be there. It can be 0 or 1. Whereas full participation means it will always be there. Okay. So if you want to say a full participation, it is shown by saying these double arrows. So I was saying, right? So this is like saying if you want B to be there, a B will only exist if A is there. Okay. So in such case, again, how we'll design? We'll have A will be separate because A is not dependent on anyone, but B will have A1 from B side. Okay. And because it always has to be there, it becomes a foreign key. So A1 becomes a foreign key. Okay. If it was not total participation, A1 could have been unique. But now what happens, because it always has to be there, it becomes a foreign key and it should not be null anytime. Okay. And let's say if it is total participation from both the sides. So for A to exist, B should be there, and for B to exist, A should be there. Then we put all of them in one single table. So because both of them need to exist for each other, so we'll put them in one single table. Okay. And for binary relationship with weak set. So this is what do you mean by weak set? Weak set means for A to exist. So sorry, for B to exist, A should always be there. So in such a scenario, again, it becomes like how we used to do for 1:m. Something similar, 1:n. So in such a scenario, A will be independent, but what will happen is B, because it needs A to exist, we'll have A also present in B. Okay, and A will be the foreign key in such scenarios. This much only. We look at certain examples, we'll try to really understand it. Okay, so this is example. So what will be the answer here? So we will need P. P will have P1. P will have P1 and P2. Let's say M is also a strong entity. M also we'll need with M1, M2, and M3. But M has a total participation on P. So then what will happen is in all the M's, P will always be there. Okay. And this side, N has a total participation again on P. So N also will have P in its table. So I think we should be able to do with three tables. So M will be one table, P will be one table, N will be one table. And N will have P in its table. M will also have P in its table, and they'll have this N1 and 2, these properties, whatever it is. right? So M will have with relation R P in its value. P doesn't depend on anybody. P is alone on its own. So P has P1 and P2. And this again, this table N, right? N will have N1, P1 and N2. P1 it will have because it is totally dependent on P. So this means total participation, and this means one is to many. So this arrow that you see means one is to many. So for every N, there is a P. So because that we have P as the foreign key. Did you guys understand?
Sir, why that R2 has two boxes, sir?
So it is like saying weak relationship. So this
Means
is a weak entity, right? So this N,
in
no, N is a weak entity and the relationship is a weak relationship.
okay,
Normal relationship is put in one box, weak relationship is put in two boxes, two ROMs.
okay, sir.
Okay.
Yes, sir.
So how will we design this? Find the minimum number of tables required to represent the given ER diagram. Let me take it chat in the screen. So A A will be a table, B will be a table, C will be a table. Agreed?
Yes, sir.
Okay. And then they are saying that A is, it should be towards this, So there is a relationship between A and C. Then there is also a relationship between B and C. But B and C have not given any number, whereas here they are given a number. Okay. So this is like saying A is dependent on B. It is so if you have an arrow towards this side, right? So it means for A to exist, B should always be there. For A to exist, C also should always be there. Right? You are seeing this arrow. So if you see up here, no? So this arrow was there, no? So this arrow is pointing towards B. So here this arrow is pointing towards B and this arrow is also pointing towards C. So that means for A to be existing, B and C should always be there. It is a, what do you say? So one to many mapping. So A many and B one. So here also A many and C one. So we'll have one table that says that has a combination of A, B, and C. So it will be, I think they'll call it A R1, R2, B, C, something like that. And it will have B1, it will have C1. And B will be a separate table, C will be a separate table. And then we'll have one more table saying the relationship between B, R3, and C, where we have B1 and C1 separately. Okay. Hmm. Correct, right? So A, B, C, uh, there are tables for them separately. A, B, and C. C is C1, C2 is there. B is B1, B2 is there. And because A to B mapping is many to one and A to C mapping is many to one, and it has said that this arrow means that from whom it is going to whom it is going, that is many to one. So for A, B will always be there. For A, C also will always be there. So it is a combination of, for A1 to exist, there is always a B1 present and there is always a C1 present. And this relation, it is they have not specified anything. It is not one to many, or it is not a dependent relation also. So it becomes you have a separate table for mapping this relation B and C. This is that R3. Okay. Let's look at another example. Okay. This is complex. So Find the minimum number of tables required to put into the evaluation model. Mm, so by looking at this, so we have uh, so B is a combination of A and C. So B to A is many to one, B to C is many to one. So if you see, right, let's take this photo. Try to see how our answer is. Okay. So you have, so if you see B is dependent on A because see many to one mapping is for B to A, and then B also has a many to one mapping on C, and B also has a many to one mapping on D. Okay. So how will B be? B will have, let's call it B R1, R5, R4. So that table will be B1, comma, B2, comma, A1, comma, C1, comma, D1. Okay. And if you see D, actually D is not depending on anybody else. Other people are depending on D. So D will have its own table. D will have a D1, comma, D2. Okay. Similarly, A is also not depending on anyone. There are other people depending on A. So A will also have one for uh, A1, comma, A2. Okay. We have done for A, we have done for D. And now if you look at C, C is depending on R3. Okay, it is only depending on R3. Okay, and it is one to many. So C will have D, one D is always there, D1, and then it will have C1 and it will have C2. Okay. So what all we have covered so far, we have covered D alone, and then we have covered B's relationship with B R1 we have covered. So R1 is covered, R5 is covered, R4 is also covered. Okay. Then A R2 C is not covered. No, so these are always separate. So what we can do is for R2 we have A and we have C. So that is A1 and C1. So this relation is also covered. And for R3, R3 is CR3 is covered, no? CR3. This is CR3. D1, D2. So this is also covered. Mm, mm, I think we did everything. So 1, 2, 3, 4, 5. 5 tables should be fine. Let's just see. Okay. So just like how we discussed, you see, so there is one, correct, right? B R1, R4, R5 is 1 because B is dependent on A, B is dependent on C, and B is dependent on D. But D is not actually dependent on anyone. D can be on its own. So D is D1, D2. Similarly, A is also not dependent on anyone. So it becomes A1, A2. And then C is dependent on D. So we have D inside C. And A is not dependent on anyone, but it has a relationship with C. So that needs to be covered. That we have covered with AC, A1, comma C. Cool. Let us look at another example. Can you guys also try this parallelly? So here, if you see, sorry, I have similarly. So E2 is dependent on E1 and E3, right? But E1 is not dependent on anyone. E3 is also not dependent on anyone. So E1 will have a separate table, A1 comma A2. E3 will have a separate table, C1 comma C2, whereas E2 no. E2 needs E1 also, E2 needs E3 also. You can see this arrow. This arrow means many to one. So what we'll have in E2, we'll have A1, and then we'll have C1, and then we'll have B1, comma B2, comma B3. Is this correct?
Yes, sir.
Let's see. So E1 has A1, A2. This has B1, B2, C1, C1. Okay. Let's take another example. So this is one more example. Okay. Let's say this, how will we do? So what all are the properties? So we have account is one. Account. First, let's see who is not dependent on anybody. Okay. Branch is not dependent on anyone. People are dependent on branch, right? So you see there is many to one mapping here, there is many to one mapping here, but nobody else is dependent on branch, correct? Sorry, nobody else. Huh? Branch is not dependent on anybody else. So what I'll do, I'll create a branch table first. Branch, where in that branch I have B name, B city, then assets. Okay. So I have this for branch. Then loan is actually dependent. Customer is also not actually mapped to anything. He is not directly dependent on anybody. So we can write customer table. But customer has some relationships, we'll take care of those relationships. Customer, we have C city, C name, C street. Okay. And then account is dependent, it's okay. And then loan is dependent, it's okay. Okay, so now let's take account, right? So account is dependent on branch. So I have to have a value there. So account has AC number and it has balance and it is dependent on branch. So I'll take a branch name. Okay. So I've taken a branch name, but account is also related to customer. How is it related? Customer is a depositor of an account. So let's call it depositor. And depositor will have C name, comma, account number. Okay. So this relationship is done. We have done a. Okay. So there is also a relationship between customer and loan. Loan we have not done. Loan is actually dependent on branch. So we'll write one for loan. Loan has a loan number, has amount, and then in which branch was that loan taken. But there is also a mapping between customer and loan. So borrower. In borrower, we have a customer name, and then we have the loan number. Okay. So customer, borrower, loan is done. So loan, this customer is done. Borrower, loan branch, this is also done. Account branch, that is also done. Yeah. So these all should be the tables. Actually, we saw branch was not dependent on anybody first. Others were dependent on branch, so we took out branch. Customer was also not directly having a one-to-many mapping anywhere or many-to-one, so we did it for customer. And then we had so the what do you say? The combination between customer and account was customer as a depositor creates an account, so we had to create one mapping between customer and account. So this actually means customer can create more than one account anytime. So customer name and the account number changes, and customer can also borrow. So loan, where is that? Customer name, loan number. So one customer can take more than one loans. This means that okay. This should this should be the answer for this. Let's take a look. Cool. Look at the answers. So account has account number, balance, account name, correct? And then branch has branch name, branch city, assets, correct? Loan has loan number, amount, branch name, correct? Borrower has the two, that is C name and L number, correct? Depositor has customer name and account number, and customer has this, correct? Right? 336. So wherever we don't have a mapping, like this arrow, we first take those, write their tables, and if there is a map, there is a relationship between two such tables, we create a new table, call it that depositor, whatever is the relationship, and then take the primary keys from both the entities. Okay. Cool. Let's take a look at another example. Okay, these people are done. Okay. So I'll stop here for a while if you people have any doubts. No? Let's,
Hi,
yeah.
we are creating one extra table, right, with two primary keys whenever we see like this depositor. So that is
Mm-hmm.
nothing but that is many to many relationship.
Yeah, it is. Many to many relationship, correct.
So like every time whenever we create table, like we have to create this separate table, or by default it will create that table, or how?
Sorry. Every time we create accounts table and customer table, you're saying will it get created by default?
Yeah, this
No,
depositor one.
we have to create. So anytime you're creating these tables, all of them should be created by you only, right? You have to create it.
Okay, okay.
Mm, got it, right?
Yes,
Tells.
got it. Thank you.
Mm, cool. Let's see if I have some more examples and we can do that. Or do we want to take examples and start from basic and design some more? Mm, so I had one D's. So let us say we want to design for a, uh, let's say we have a, what is the most common example that you guys can think of? If I want to design a ER diagram, would you have any idea?
Library management system.
Okay, library management system. Cool. So in library management system, what all will we have? We
Student,
have
librarian,
we have a librarian,
student,
Instead of calling student, let us call user.
Yes, user.
And what else do we have? We'll have books.
Books.
We'll have authors.
Yes.
We'll have sorry, I'm writing same number 3, 4, 5.
Department, sir.
Uh, department. Okay, so you are
String.
college, no? Uh, which department a book
We
belongs to?
we can say string, sorry, string.
Stream.
Is it?
Okay. Or
Uh,
we'll call it, what do you say, category
Subject. Category or subject.
or genre?
Catalog.
Right.
What is the spelling? I'm not sure. Let's assume that is a spelling. Genre. And then what else do we have? Genre wouldn't, it will not become an actual. Okay, let's keep it. Let's see. Then users, books, and let's say we also have shelf.
Library card. Okay. You will win a library card.
So user will have a library card. Let's say. Okay.
Yeah, yeah, yes.
Shelf, because let's say if I ask some librarian where is this, so shelf actually exists in a library, right? So this book is in this shelf, right?
Yes, sir. Yes, sir.
Okay. So now if you have to start designing this, uh, so let's say initially we have books. Okay. Books, what all books will have? Books will have, it will have its ID. Okay. And then it will have its ID is, let's say, let's not confuse it. Let's call it name, ISBN number. Okay. And the book will have its name. What else will a book have? Let's say pages. And if I take author, and then uh, say if I put a box around this author will have name,
Publish date.
published date. Okay. Pages, published date. Cool. So author has a name. Let's say he has a date of birth. This much is enough. So what is the relationship between author and a book? Author
Name.
publish. Author publishes a book. Can I say that? Or easy, why writes a book? Author writes a book, correct?
Yeah, that is a
Then,
relation.
mhm,
Yes, sir, that is a relation. Author and
yeah.
book.
So this is the relation. So now for a book to exist, can I say books will always be okay. So author to book can be 1:many, right? I mean, many authors. No, many authors cannot write one book. An author can write many books, correct?
Yes, sir.
So what we could have is okay. So I'll do a total participation and I'll say this. Okay. So this what makes for a book to exist, there should be an author. So there is a total participation. And I'm saying books will always need an author. Without an author, books cannot exist only. Right?
So why we make book weaker section in a weaker section, double arrow,
Book is
double.
not weaker. So this double arrow is not meaning weaker. This double arrow is total participation.
Okay. Okay.
So what I'm trying to say is, for a book to exist, there should always be an author, no?
Yeah, that I understood.
Okay. So for now, let us assume only one author writes a book. Okay, it will get complicated if we say a book can be written by 3, 4 authors also, no? Right. So let's say in our library, books are written by one author only.
Okay.
Okay. So then we have users. Okay. So what do users do in a library? Users borrow. And a user can borrow, cannot borrow. It is not compulsory, right? Is this relationship correct?
Yes, sir, correct.
Okay, so users is done, books is done, authors is done. Genre,
So the user can buy more books, more than one book. So
yeah,
there
correct.
should be relation like one to many.
So user can borrow any number of books, right? So it is not one to many, many to many. So one user can borrow. So it is like saying a user can not only borrow one book, he can borrow more than one book, or he may not borrow also, no?
There's take.
So it is like saying a user may be borrowing a book or he may not be borrowing a book at all. So then you don't have a total participation, one thing. And it is not a it is not one to many mapping also. Right? At different points in time, different users can borrow different books, no?
Okay, sir.
Okay. So librarian, how will we fit librarian? Let's say librarian we will not keep for now. Librarian, it will basically got to do. Okay, so let's say we have librarian also. So what librarian does, librarian helps in borrowing a book, right? Correct, no?
So
Yes, sir.
librarian is a owner.
Issues. Librarian issues books to the user. So you borrowed the book. Who helped you borrow who was there looking at that time when you're borrowing the book?
The librarian, the owner of the librarian.
So what will be the relationship? Book is borrowed by,
Here.
let's say we add this person also here only, okay? So if I add this person also here only, and can we say without a librarian you cannot borrow a book? So then what we can say
There
is,
should be a person who is always available to give us.
sorry.
Yeah, there should be a person who always give us, who can give us the
Correct,
access
correct, correct,
to take the
correct,
book.
correct, correct, correct. Mm, I
Access
think
to book.
so. Borrow only. We'll call it borrow only. So he is also connected to borrowing. Okay. And then we have last thing is shelf. So book exists on a shelf. Okay. So we can say book exists on a shelf, right? But then what kind of condition will be put here? So which book exists on which side? One book cannot exist on different shelf.
Librarian can keep order to self to give the book for the to the user.
Librarian can? Sorry.
Can librarian can order the self to
Shelf
take
is
a book. Yeah.
shelf is like this. Shelf मतलब जहाँ पे बुक्स रखते हैं ना वो कबाड़ क्या बोलते हैं उसको
Okay.
अलमारी जैसा होता है ना दैट इज शेल्फ इट्स नॉट सम पर्सन
Okay. Thanks. Okay.
okay, books will exist on a particular shelf so
Hmm.
mm,
So,
but it will not be a many to many mapping. It should ideally be one to a book will always be on some shelf, right?
yes, sir.
So then no so many books can be on one shelf. So one shelf is a big rack, right? So
Yeah,
you
it
can
should
have
be some, yeah,
you can have many books in one shelf.
table number, self number. Yeah.
Let's keep shelf only. Shelf one shelf can have any number of books. So the relationship between books to shelf is uh, one shelf can have many number of books. So it is one to many. So if it is one to many, let's say, can I put it one to many? No. One book, many books in one shelf. So from book side, it is many to one. So I can say, uh, I'll say this.
Without self, book cannot exist.
Not necessary. Book can be borrowed, right? So if it is borrowed, it will not be there on the shelf, right? So we have one more genre. So how will we put where we put genre? We'll put it here. Genre book belongs to a right. Book belongs to a genre. Correct. So again, it is it's a one-to-one mapping basically, saying uh, one book belongs to one. Let's assume one book only belongs to one genre. So how will we map it? I'm also not a prof in this. They used to discuss this in college time. How will we map this now? So you have books and you have genre. So many books can belong to one genre, but one book will always belong to only one genre.
Sir, genre can be a property of book. Like we can
Yeah,
add we can add the genre type, and we add this with the name, pages, and publish date
yeah, that is also
as a
fine. Yeah,
property.
Yeah, I feel that is much better. Instead of having here, you have a genre here.
genre
Yeah,
type.
yeah, makes sense. So then if you have to convert this into a table now, how will we do it? Let's say you have books is one table. Author is one table. And then you have shelf, which is one more table. And then you have librarian, which is one more table. And then you have, okay, so author does not have any mapping, right? Initially we'll write for author. Author has name, he has date of birth, and yeah, that much only. But books are mapped to an author, and books are also mapped to a shelf, right? So there's a total participation of books on author, but not total participation on shelf, but there is a mapping, right? So in books, what we can have is they'll have ISBN, they'll have name, they'll have genre, and then they'll have the author ID, call it AID, and then they'll have shelf ID. Okay. And say this, right? Because book depends on author and it depends on shelf. And say this. So then shelf doesn't actually depend on anything. So I can say shelf is normal. Let's say we have the shelf ID, and then let's say we have its location, and then let's say we have its size, and let's say we have how many empty is there. Okay. Librarian will have again normal ID, name, so on and so forth. And then so borrow, how many people are dependent? So librarian is there. And then you have the book that was borrowed, and then you have the user, right? This can be one table. Okay.
Yes, sir.
And here
Yes, sir.
the key becomes book and user, primary key. It's a combination of these both. So if this user has taken this book, he cannot take it again. Okay. Let us
Yes,
look at
sir.
some examples online. Wait, how would people have designed? I think we can still do better. Library ER diagram examples. Not fully. How they have done. So you have reader, and you have books, you have publisher, you have authentication system, staff, reports, manages, and you have maintains, books, readers, reserve, return date. So they have how many types people? Reader is there, books is there, publisher is there, staff is there, there is authentication system, and there is reports. Okay. And reader can reserve a book or return a book, and this has certain properties. Books have certain properties, and books are published by publisher. And then password is everybody has a staff has a password. Okay, manage. Let's take a simple one. All are different. This looks fine. So you have so these are called crow bars. Okay, so this is also used for one to many, many to many kind of mapping. Okay, so we have a book. So instead of author, okay, they have author here. They have publisher instead of author, and then you have a member. Member borrows a book, and it is issued on some date, and book is published by a publisher. Almost similar to what we did, right?
Yes, sir.
Okay, cool. So I think that much is enough for ER diagram. So you can have a look at online articles and see how to do, or you can practice on your own and then try converting ER diagrams to tables. Okay. I had certain, I found certain good PDFs online. I'll share those PDFs with you. So this had a lot of other examples of how you would design these diagrams. Yeah. So why we do? So we have to understand the reason why we do this. So it becomes very easy if you draw an entity ER diagram. Right? It becomes very easy to then convert it into a table if you have correctly mapped all the relations and all. Or else if you start directly from a table, it is very difficult to get a big picture and see from where to start. Okay, cool. So we'll start what normalization is. I'll give certain basic examples and we'll continue tomorrow. Okay. So whatever we did so far, right, it is a top to bottom approach. So we are starting from the whole image, like what is library, what all people are there in library. Then we are designing a diagram, and then we are coming all the way to the bottom to what do you say? All the way to the bottom to what are the individual tables and all. So this is top to bottom entity relation modeling. So bottom up approaches, we start designing the tables and then we start enhancing the tables and trying to go up all the way to the top. Okay, so that is bottom up approach. So bottom up approach is called as normalization. Okay. So the reason, so even if you go always, if you go from top to bottom, but even at the when you come down, right, you might have chances where you are repeating the data across 2, 3 tables. So how do we ensure that we are not repeating that kind of data across 2, 3 tables? We use normalization and do that. Okay. And you know why we don't want to repeat the data, right? So one is it becomes very difficult to update, delete, and all. Update, delete, even reading it becomes very difficult. And the other is we don't want to store unnecessary data. Okay. So data duplication, yeah, nothing special. Again, normalization. What we do, we take big tables and then we restructure them such that they are not repeating and it is data is unique across everywhere. So there are different forms of normalization. We'll see what is. So they are called first normal form, second normal form, third normal form, uh, fourth normal form, and so on. It exists till 4, 5. If you know top 2, 3, that is also fine. Okay. So let me give an example. So I'll show you a table. Tell me what is the issue with that table. Okay. So I have a table. Let's assume. Too much. Okay. So let's say name, and let's have 4 numbers. Okay. And say I'll take Guru, and I have 3 phone numbers: 70123458971165. So 6 numbers. Okay, 7 number phone number, and then 1317865. Okay, and let's say Rishikesh. Rishikesh has 2 phone numbers: 345134786. So what are we doing here? So there is one ID and we have a lot of phone numbers. So not necessarily phone number, you can also have address. So you have a name and you have an address column. and instead of having one address, you're having 2-3 address for the same person in one row only. Okay. Or let's say you have a name, you have a person, and then you have subject, and then you have all the subjects inside. In one column only, you have 4-5 subjects. So do you see what is the problem here? So let us say I say, so I am a customer. I come to the company and tell I am no more using 70123455. Delete this phone number for me. So then what will you have to do? What do we have to do then? So we have to go search. We cannot directly search. I'll have to go find Guru's name, and then I'll see, does the name exist? Does the number exist inside this, right? And then I'll have to take out only this and then put all of this back together, right? So instead of this, what we can do a better way is, I have a table, and instead of storing everything in one, right? So what I do, I store it in a different columns, different rows. So what happens? So then it becomes, so we'll have a name. Okay. And then we have phone number. And now for same me, you have 1, 2, 3 is one phone number. 7, 8, 1, 4, 5, 6. Okay. So in a case where, let's say you had this and you also had ID, say, let's say you had what all of their name, let's say you had date of birth. So then what you will do, you'll take out this phone number column from here, and then you'll make a separate table and have one row for each phone number that I have. Okay. So this way, what I'm doing is, whenever, let's say in future, if I want to delete a phone number, it becomes very simple. So I'll just do where phone number is equal to whatever is the phone number that they've given, right? And updating numbers also become very easy. Adding also becomes very easy. I just have to directly come and add here one. Or else what we'll have to do, I'll have to come, take out all the phone numbers, remove whatever is there, modify it, and then add it. It becomes very difficult to search also, right? So what we should, at any time, if you have a multi-valued attribute, so these are called multi-valued. If you saw even in while doing the entity relation diagram, right? We said if there is a multi-valued attribute, create it in a different table, right? So similarly, what we should do even when we see a table which has multiple values in a single column, you have to break it down and add it into different single row. You have to break it down and add it into different rows. Okay, so this idea is called as one normal form, one NF. Okay, let's see example. So here we have, okay, so maybe this is the user ID, and sorry, we have how many books that user has borrowed. So here there are 3 books, and this user has only borrowed 1 book. So now it becomes very, if I have to just answer a single query, has a user 1 borrowed B30, B40? Okay, then what I'll have to do, I'll have to go to C45 and I'll have to get all his books and then see if B40 exists inside this one. But if they all were separate, then it would become very simple, like saying, does this row exist? C45, B40, does this combination of a row exist in that table or no? It doesn't exist, we say no. Okay, so how do you do it? You will break it into like this. Okay. So this is what is first normal form. So we look at the next is, that is 2NF. So what is 2NF? Okay. So let us say,
Sir.
Yeah.
Sir, here we are increasing the number of rows in table, so that will not affect on storage or anything. Increase
no.
storage.
So this is fine. So you're only adding the ID, right? You're not adding anything extra. So only ID is there. And if you club it together, no, it becomes very difficult to search or
Yes,
find
yes.
and all, right? So by doing this, what you're doing, you are storing it in such a way that it is very easy to update, delete, search, and all.
Mm. So will that increase storage or not, sir?
It will
Particularly
increase.
in the it
It
will increase.
may not be huge, but it will increase.
Okay, okay.
Okay, but the advantage is everything else becomes very easy.
Yes, sir. Yes, understood.
Okay, so let's say if you had flight and if it is running for certain days, and then what you do it this way. So in entity relation model, whatever entities have multiple values, so for them we convert them into a different table. Okay. So then comes second normal form. So when do we say a table is second normal form? That I'll show you. Okay. Let's take this example. So okay. So this is a table saying which book is written by whom. Oh, no, no. So there's a table saying not which book is written by whom. So who has requested a book? Okay. So you can see so book number, patron is a person who has requested the book. What do you think is a primary key here?
So mobile number.
No, right? Mobile
Phone
number is repeating.
Book
So
number.
the situation I'm telling. So a book has been borrowed by a user. So what is unique here? What a combination? Primary key need not necessarily be one only. No? It can be more than one also. It can be a combination of values. So can I say book number and patron is the primary key? Because let's say if I borrow a book number B, if J Fisher has borrowed book number B3, he cannot come and borrow book number B3 again, right? So it is unique. Correct?
Yes, sir.
Others understood. Because this is like saying, let's say Suraj comes and borrows B3 book once, so he cannot come and borrow B3 again, right? So there is already borrowed the B3 book. So this becomes the primary key. So this is the primary key, but if you see phone number is mapped to what? Phone number is mapped to a user. So this phone number belongs to whom? This phone number belongs to this person, patron. So, correct, right? So what is happening is, let us say I have to, J Fisher told I want to update my phone number. What are we doing here? If this was our table, what would have we done? We would have updated it two places because so J Fisher
Yes,
is here,
sir.
J Fisher is here. So his phone number we're updating twice. So what is happening is, sorry, this phone number, right? This phone number should not be here. Why? Because this itself is enough for me to say which book was taken by which person. Correct, right? So how if I was to redesign this, how will I redesign it? It would become something like this. So this would be one table, and this will be another table. Sorry. So the ideal way to design this would be, so book and patron is on one side and phone number is related to patron. I don't have to put it in this with this book. So now let's say if I have to update the phone number, I just have to come here and update it one place. So what is happening here is a subset of this, a non-primary key value. So we have primary key, and then let's say this is non-primary. Okay. So a non-primary key value is dependent on a subset of this primary key. So if I was to say, what are primary keys here? It's a combination of book number and patron. Agree? And non-primary key is phone number. That's right. And this phone number is only dependent on this patron. It is only dependent on the subset of this whole primary key. So we should not have a structure like this where a non-primary key is dependent on a subset of the whole primary key. If it is dependent, it should be dependent on both of this. So like here, if I would have a borrowed date, no, then it would depend on both of this book number and patron. It cannot exist without book number and patron together, right? So whenever we find a situation where a non-primary key in a table, a composite key, you can say, in a table is dependent on a subset of the primary key. Okay. In such scenarios, what we are supposed to do, we are supposed to break down this and separate out the non-primary key and this subset of the primary key into another table like this. Then we say that the table is in 2NF. It's in second normal form. Okay. So if I was to give you a different example, say second. Let's say here. So here, if you see, student ID. So here, what is the common name? What is the common? What can you say is the primary key? So this table is basically to identify which student is assigned which project, right? Student ID, project ID. But you also have the student name and project name. So here you can say primary key is a combination of student ID and project ID, right? And non-primary key items are student name and project name. But if you see, student name is it directly depends on a subset of the primary key of this table, that is student ID. It doesn't actually depend on this whole both together value. It is only mapped to the student ID, right? And also project name is not fully mapped to the whole primary key. It is only mapped to project ID. Right? So what is happening? A non-primary key is mapped to a subset of the primary key in this case also. So then in such cases, what are we supposed to do? So this this becomes one separate table. And then you have one table saying student ID, student name, and another table saying project ID, project name. So it would be here. They've done it like this, yeah. Student ID project. Okay. So they've taken this project different. Even better way to do this would be to, even remove this student name and say, keep a separate table for student ID and student name. And you have a mapping between student ID and project ID. I think we'll stop here for today. I'll continue in the next class. Very few topics that are left. We'll try to finish off in the next class and end the course. Okay. So if you see, we have finished. What all have we finished? So definition, if you see, it is saying a non-primary attribute of a table is an attribute that is not part of any candidate. Okay. So not part of any candidate table. A candidate key is the minimal. So okay, fine. A table is in 2NF. No non-prime attribute is dependent on any proper subset of any candidate key of the table. It's a little bit, what do you say? It will be very difficult to read this and understand, but the idea is like this. So if this is the primary key, and then I have other columns in this table which depend on a subset of the primary key, then the table is not in 2NF. You have to break it down to make it 2NF. Okay. So here the example is, okay, this is the example we saw. So if you have table is not in 2NF, then you'll have a problem for insert anomaly, update and delete anomalies and all. So then we convert it to 2NF, it becomes like this. Okay. So we look at 3NF and then we'll see BCNF tomorrow and we'll finish off whatever are the other topics remaining. Okay. This is done. We also looked at, I think, enough number of case studies, whatever is remaining from this side. So we'll see how to tune SQL queries. Maybe we'll look at little real life examples, and I'll try to touch upon how databases work, a little bit of it, and then what is NoSQL databases. You'd have heard a lot about NoSQL database, and I'll try to cover that also.